To introduce the last speaker for this term, Eric Primozic from the University of Alberta, and he'll speak on Motivic cohomology and infinitesimal group schemes.
Thank you. So I'll start by saying what these words and notation in the title mean. So fix a prime P. And for a scheme over Fp, you have the Frobenius, which is just given by the pth power on the structure sheaf. And so for a group scheme over Fp, then I want to define the relative Frobenius. So you define G1 by the following square. You have Frobenius on K. And then you have the structure map from G to spec K. And then you take pullback to get G1. Then you define the relative Frobenius. By taking the map from G to G1. And then we define the Frobenius kernel. The first Frobenius kernel is just, so this is a group hom, or morphism of group schemes. So you define the first Frobenius kernel as a kernel of this. And then you iterate it to get the higher Frobenius kernels. Note that then probably have to assume G is like a finite type, but if G is defined over Fp, then you can identify G1 with G. And you can basically then think of this relative Frobenius as just being the pth power on coordinates. So let's look at, this holds, for example, if G is split reductive. So some examples, if I take GM, then the nth Frobenius kernel is just the group scheme of the p to the nth roots of unity. If I take GLN, then I can describe the rth Frobenius kernel as just being the spec of, so you take the ring of GLM, mod the xij to the p to the rth power is equal to delta ij. So these schemes appear in representation theory and number theory. I'll recall a couple of calculations on the group cohomology. So assuming that G, I forgot what assumptions are necessary. Maybe G is simple and simply connected. Then the cohomology ring of G1 is identified with the functions on the coordinate ring of the nilpotent cone. So N, where N contained in the Lie algebra of G is the nilpotent cone. And this was proved by, say, Friedlander partial. With some bounds on P, depending on G. And by Anderson and Janssen. Assuming that P is greater than the Coxeter number of G. And then more generally, we have that for the higher Frobenius kernels, there exists a homeomorphism.
What do you mean by bounds on G?
I think it's something like P is greater than, or sorry, yeah, P is greater than 3 times the Coxeter number minus 2 or something like that.
Thank you.
It depends on the group, I think, too, by the way. It's like 3H minus 2 and then might be 2 times, well, obviously Anderson Janssen improved it. The publication dates are sort of out of chronological order. Then for the higher Frobenius kernels, there exists a homeomorphism of topological spaces from spec of the cohomology ring to spec of a certain ring, spec of the functions on VR of G, where VR of G is an affine skein parameterizing morphisms from GA of R, so infinitesimal one parameter subgroups of G. And so this is proved by Suslin, Friedlander, and Bendel. In 1997. So I want to consider sort of analogous results for Motivic cohomology. They'll look very different from what's going on here. It won't be as difficult. So I'll start by saying a few words about Motivic cohomology. The cohomology theory involving cycles on algebraic varieties. So fix a field F and X over F, a smooth scheme of finite type and all the usual assumptions. Then we have a bigraded cohomology theory given by Motivic cohomology. And it's isomorphic to, maybe a more concrete way of thinking about it is it's isomorphic to higher Chow groups. So you have that Motivic cohomology in degree I and weight J is isomorphic to codimension J Chow group. And then you have this shift here, 2J minus I. So higher child groups are just given by the homology of Bloch's complex. So that's given by I think that's how you spell his name. So that's given by the homology of the following complex. You have, so X cross the algebraic Q simplex, and then sitting inside of that, you have cycles that meet the faces properly. So codimension are cycles of X cross delta Q that meet the faces properly. And so when you have them meeting the faces properly, you can take an alternating face map. And higher child groups are just the homology of this complex. So in particular, we have the following vanishing of Motivic cohomology. When degree is greater than 2 weight. So you have HIXCJ is 0 if I is greater than 2J. Okay, so that's Motivic cohomology of smooth varieties. Now we want to generalize that. So I want to talk about the geometric classifying space of a group. So this is due to Totaro and Morel-Voivodsky. So take G over F, where F is a field, to be a flat affine group scheme of finite type. And here we're going to allow non-smooth group schemes, since that's what this talk is going to be all about. So you can still make the following definitions. The idea is that we want to approximate. So a classifying space doesn't exist as a variety, but we want to approximate BG by smooth FPPF quotients. I'll just write quotients. So suppose that we want to define Motivic cohomology BG classifying space with some weight J. So we take you can find a representation, faithful representation G into GLV, such that GX freely on some open subscheme of V. So we want to take the codimension of S large. So for some closed G invariant S inside of V, and such that the quotient exists. So we assume U mod G exists as a scheme. maybe quasi-projective as well. But then we define, oh yeah, I forgot to tell you assume that codimension of S and V is greater than J. So then we define motivic cohomology of BG with weight J to just be the motivic cohomology of these quotients. And this is a well-defined construction. So for some examples, the motivic cohomology of BGLN is just a polynomial ring over the motivic cohomology of the field in the Chern classes. And then something that'll be important for us is if I take characteristic of the base field to be P, so take K to be F here, then the motivic cohomology of B mu P with mod P coefficients is isomorphic to the motivic cohomology of the field and then with generators U and V such that U squared is 0 and so V is the first Chern class and U is an element in H11 such that its Bachstein is equal to V. Okay. So now I want to consider motivic cohomology for Frobenius kernel. So take G over basial K split reductive. Probably have to assume K is perfect, but so what can we say about the motivic cohomology of BGR? So take a quotient that approximates BGR. Then we want to use that the Frobenius, the rth Frobenius is trivial on GR. So you can factor the Frobenius as follows. You have U mod GR, and then you have the rth Frobenius. So Frobenius raised to the rth power. That factors through U. You should think of U as being contractible. So I'll call this the quotient map. So in particular, if you have a reduced cohomology class, so take an element X in the motivic cohomology of BGR, And then you can pull it back to a point. And assume that X maps to 0, so it's a reduced cohomology class. Then from this commuting triangle, we get that 0 is equal to Frobenius pullback of X. But we know you can, it's known what the Frobenius does on Motivic cohomology in terms of weight. So I'll put a weight in here, I'll call it J. So on weight J Motivic cohomology, the Frobenius just acts by P to the J. So this is equal to P to the RJ times X. So this tells you what all the P torsion on the Motivic cohomology BGR is. So it varies with weight. And then you can get a bound on the torsion in terms of G as well. So we're going to consider then the goal of this talk, or one of the goals, is consider Motivic cohomology with Z mod P coefficients. And the guiding example for us will be that the Motivic cohomology of bu mu P is isomorphic to the Motivic cohomology of BGM tensored with the Motivic cohomology of GM. And the tensor product is over the Motivic cohomology of the base field. So we want to generalize this. So we have the following result, which is that, so take G over K, split reductive. With the characteristic of the base field, a non-torsion prime. Should be K. And I'm going to define what that is in a minute. So assuming that P is a non-torsion prime, then we can prove that the Motivic cohomology of BGR, the R-Frobenius kernel of G, is isomorphic to the Chow ring of BG. This is going to be a polynomial ring tensored with the Motivic cohomology of G. So this is isomorphic to a polynomial ring tensored with an exterior algebra. Let's see where, if I take, so yi is in degree I in the Chow ring, so it's in by degree 2ri ri. And gi is in by degree 2ri minus 1, ri. Where ri is a fundamental degree. And we also have that the the integral Bachstein evaluated at GI is equal to P to the R times Ri minus 1 times Yi. So integral Bachstein goes from, let's see, H to Ri minus 1 BGR with Z mod P coefficients to H2Ri BGR with integral coefficients. And you can say this condition in other ways too, probably involving higher Bachsteins. So where R1 to Rm are the fundamental degrees, allowing what do you call it? Repetitions too. Okay, so I'll briefly remind you what the torsion index and torsion primes are. So take G split reductive and take a Borel inside of G. And the split torus. And dimension of the flag variety, we'll call N. Then there's different ways to define the torsion index, but they're all equivalent. I'll give one. So we have a natural map given from CH1 of BT to Picard group of G mod B. And then taking products, we get a map from CHN of BT to codimension N child group on the flag variety. And this is isomorphic to Z. So then we say the torsion index is the co-kernel of this, the order of the co-kernel. And we say a prime P is a torsion prime for G if it divides the torsion index. And we say it's a non-torsion prime if it does not. So for these special groups, the like GLN, symplectic groups, SLN, the torsion index is just 1. But if every single prime is realized as a torsion prime, since P is always a torsion prime, for PGLP. But if you assume that G is simply connected and simple, then the only possible torsion primes are 2, 3, and 5. So for example, I don't know, 2 is a torsion prime for the spin groups in high enough dimension. I think n greater than 6. And 5 is a torsion prime for E8. Okay. So that's the definition of torsion primes and torsion index. Now I want to introduce the main tool that we use to compute the Motivic cohomology rings. That is the Eilenberg-Moore spectral sequence. So I did introduce some notation. So for a bigraded ring, commutative ring probably, yeah. So for a bigraded ring R and a bigraded R module M, M1, M2, what do I want to say? M and N. Then we define Tor. We just introduced this notation for Tor for the different parts. So Tor I Qj of Mn is the Qjth bigraded piece or part of Tor I Mn. Okay. Then we have the Eilenberg-Moore spectral sequence. And in this generality, it's due to Krishna, though there were some special cases considered by people earlier. So take G over K, K is a field split reductive. And take it acting on a smooth scheme. Then there exists a left half plane spectral sequence. With the following E2 terms. So it's E2 LQ is equal to Tor of minus LQ. So it depends on J. Just pick J. So the following E2 terms, so Tor of Chow ring of BG, and then of Z, and then the G equivariant motivic cohomology of X. And then you have to invert the torsion index. And it converges to the regular motivic cohomology of X. Again, with the torsion index inverted. Okay. So we want to apply this to, we're interested in Frobenius kernels. So we want to apply this to the fibration given by BGR maps to BG, and then the fiber is just G. So here then the spectral sequence will look like, and we're going to take it with mod P coefficients. So assume P is non-torsion. Then we want to consider the spectral sequence for this vibration. So it looks like Tor of child ring BG, mod P, and then integers mod P. Then you have Motivic cohomology of BGR. With mod P coefficients. 1, 2, 3, converging to the Motivic cohomology of G. Okay. So I'll say a few words about what goes into the calculation. So it uses the so I'll say what goes into showing that the child ring of BGR is isomorphic to the child ring of BG, mod P. Sorry, this should be, I missed it. So we're going to use the calculation, the cohomology for the p-th roots of unity. So take a split torus. T sitting inside of G. Then we have the following commuting diagram. So we have child ring of BG, mod P, then it maps to, you can pull it back to child ring of BGR. And then you can map child ring of BG to child ring of the torus. And then you can pull that back to child ring of BTR. So a product of copies of mu P to the R. So we know that since P is a non-torsion prime, this map is injective. So its image is just the invariance of the Weyl group. There you go, mod P. And then from the calculation of the P to the nth roots of unity, we know that this bottom map is injective. So that tells you that the top map is also injective. What about surjectivity? We use the Eilenberg-Moore spectral sequence. So with so we have E2 LQ as I wrote above, and it converges to HL plus QG of Z mod P of J. And here we use that P is a non-torsion prime. This implies that the child ring of G mod P is just trivial. It's V mod P in codimension 0. So this then tells us that 0 is equal to the following Tor terms. So Tor of 0 2jj. So this is E0 2j2. And then, so this is 2jj. When you take when you take something bigger than 2j here, you have vanishing of Motivic cohomology. So this is equal to the child group of G, and that is 0. So then that tells you that the child ring of BG mod P maps surjectively onto the child ring of BGR. So hence it's an isomorphism since it was injected. All right. And then the rest of the proof is sort of playing around with the spectral sequence. So rather than talking about that, I want to talk about comparing to other cohomology theories. So the one I'm going to be interested in is a tau motivic cohomology. Also known as Lichtenbaum cohomology. And here it's important to note that it's not a homotopy invariant cohomology theory and positive characteristic. You have to be careful on what you mean by a tau motivic cohomology of classifying space if it's not a homotopy invariant theory. So to do this, we're going to consider sort of a different object than the classifying space. So I want to talk about mod P tau motivic cohomology, assuming that the base field again is characteristic P. So the starting point for how I want to define this is if I have X over K smooth scheme, smooth variety, then Geitzer-Levine proved that there's an isomorphism between weight J motivic cohomology, so complex representing weight J motivic cohomology. So think of this as being Bloch's complex with the logarithmic Hodge-Witt sheaf. Shifted by minus J. And this is in the derived category of sheaves on X in either the Zariski or Atala topologies. So this is logarithmic Hodge-Witt sheaf. So it's a sheaf, so I think it makes it easier to work with to define sort of cohomology. So for G over K, a flat affine group scheme of finite type and so on, we consider the abelian sheaf of logarithmic Hodge-Witt forms on the big Ital site of the classifying stack BG. So I think in older papers, this object here is usually only defined for smooth schemes, but you can also do it for arbitrary FP schemes. So I believe it is valid to define this on the big Ital site. So you're gonna have to deal with potentially non-smooth smooth schemes. And then define weight. So define the Ital-Motivic cohomology of the classifying stack to just be the Motivic cohomology of this sheaf. Now we want a comparison map from the Motivic cohomology, or a cycloclass map from Motivic cohomology of the classifying space to the Ital-Motivic cohomology of classifying stack. So this is the classifying space defined by approximating it by quotients, and classifying stack is something different. So how do we do this? Take a quotient that approximates BG, the classifying space. So basically, so that the weight J Motivic cohomology is weight J Motivic cohomology of U mod G. So then we have G torsor. And so this gives a map, should probably use a different notation, from U mod G to the classifying stack. And so how do we get a Ital-Motivic cohomology? Well, the Ital-Motivic sheaf cohomology can be defined, computed from a cover of BG, the stack. So it can be computed from the Church nerve. Of U mod G to BG. So this is using that this is smooth and surjective. So map from a scheme to a stack. So the Church nerve is given by the following simplicial scheme. Just U mod G and then U squared over G and so on. And then the Eilenberg-Motivic cohomology in degree hi minus j of Bg is equal to the sheaf cohomology of this simplicial scheme. Okay, so how do we relate this then to the homotopy invariant Motivic cohomology of the class-defined space? You can consider the sheaf cohomology in the Zariski topology of the Chechnerv. And by homotopy invariance of Motivic cohomology, this is isomorphic just to the Zariski cohomology of U mod G. And then since U mod G is smooth, this is isomorphic to Motivic cohomology of U mod G. Okay, so then we get a comparison map as follows. You have Motivic cohomology of the class-defined space. So that's isomorphic to Motivic cohomology of the quotient U mod G. And this is isomorphic to the sheaf cohomology on the simplicial scheme, the Chechnerv. And then to get a Eilenberg-Motivic cohomology, we do the change of sites map. And then the Chechner computes the Eilenberg cohomology of the class-defined stack. So this is class-defined stack. And then this is a well-defined map. So it uses that the Motivic class-defined space is well-defined. And that the sheaf cohomology of the class-defined stack or maybe I'll write hi minus j. It can be computed using any smooth surjection to the stack. Smooth x to bg. And then to wrap things up, I'll just say, so I think for So mapping from motivic cohomology with Z mod P coefficients to a tau motivic cohomology of stack. I guess I can show it's injective for some examples. So it's injective. But yeah, I'll take the Chow group. So it's injective for GM, as you might expect. And then from there you get it's injective for split torus. And it's also injective for mu p to the n. And then from there I can show that it's injective for the R Frobenius kernel. So where G is split reductive with P a non-torsion prime for G. I'll stop there.
Thank you very much, Eric. Are there any questions?
I guess the obvious one is, can you compute the whole atal motivic cohomology in sort of easy cases, like, you know, for GLN, maybe or split reductive groups, or maybe, I don't know if that's reasonable.
I guess I don't know how to compute any atal motivic cohomology at all at this point. Other than by comparing, I can only show things are injected by comparing it to what we call Hodge cohomology. So you have the inclusion of logarithmic J forms. So you can go from a tau motivic cohomology let's do W1 to Hodge cohomology, which is something that's more computable. At least for split reductive groups. But yeah, I don't know how to calculate full example set of a tau motivic cohomology.
Are there other questions?
I have a pretty maybe naive question, but did you have a chance to look at modular cases? No? Well, I guess, say, I don't know, say at modular primes, at torsion primes.
Oh, yeah, I wasn't able to get anywhere with those. Yeah, I did try. I don't have anything interesting though to say about those.
Other questions? Okay, if there are no other questions, let's thank the speaker again. And this is our